let's start with a big idea. The Big Bang. We all have a picture of it in our heads. A single point, an incredible explosion. Everything in our universe rushing out from that one moment. And for a long time, that was the story. A good story, too. It explains a lot. It explains why galaxies are moving away from each other. It explains the leftover heat from the early universe that we can still detect today. But it's not the whole story. The simple picture of a single explosion has some problems. It's big ones. Problems that made physicists scratch their heads for years. These weren't small details. They were fundamental cracks in our understanding of how everything got here. And the solution they came up with is wild. And it's an idea that suggests our entire universe, everything we can see and ever hope to see, might be just one tiny bubble in a vast, foaming, cosmic ocean. An ocean of other universes. So, did our universe bubble off from another one? The idea sounds like science fiction, but it comes from real science. It comes from trying to fix those cracks in the Big Bang Theory. To understand it, we have to go back to those problems. There are two main ones we need to talk about. People call them the horizon problem and the flatness problem. They sound complicated, but the ideas behind them are pretty simple. First, the horizon problem. Imagine you're in a huge cold room. You put a thermometer on the east wall and another on the west wall. You wait a while, and then check them. They both read exactly the same temperature. You might think, okay, the room just settled to an even temperature, the heat spread out. But what if I told you the room was so big and you only waited for 1 second? There hasn't been enough time for heat to travel from the east wall to the west wall. There's no way they could have communicated with each other to even out their temperature. It would be an incredible coincidence. Our universe is like that giant room. When we look out at the oldest light in the cosmos, the afterglow of the Big Bang, it's called the cosmic microwave background. And it is shockingly uniform in temperature everywhere we look. The patch of sky in one direction is almost the exact same temperature as the patch of sky in the complete opposite direction. But back in the early universe, those two patches were separated by a vast distance. According to our standard Big Bang model, they were never close enough to have ever exchanged heat or any information at all. They were outside each other's horizon. So how did they end up at the same temperature? It's a coincidence on a cosmic scale. A coincidence so big that it probably isn't a coincidence at all. Something else must have happened. Then there's the flatness problem. This one is about geometry. We're all used to the idea that space has 3 dimensions, but that space can be curved. Einstein showed us that mass and energy bend space-time. The universe as a whole has a shape. It could be curved like the surface of a sphere. If you travel in a straight line, you end up back where you started. It could be curved like a saddle, a shape that bends away from itself, or it could be flat, like a giant infinite sheet of paper. Here's the strange part. All our measurements show that our universe is incredibly, mind-bogglingly flat. It's not a little bit curved. It's just about perfectly flat. This is also a huge coincidence. For the universe to be this flat today, it had to have started out with a level of flatness that is hard to put into words. It's like throwing a pencil into the air and having it land perfectly balanced on its tip. And not just once, but every single time. Any tiny deviation from perfect flatness at the beginning would have been magnified over 13.8 billion years. A slightly closed universe would have collapsed back on itself long ago. A slightly open one would have expanded so fast that galaxies and stars never would have formed. Our universe is balanced on a knife's edge, and the standard Big Bang theory has no explanation for why. So, we have two major puzzles. A universe that's too uniform and a universe that's too flat. It's like arriving at a crime scene where everything is just a little too perfect. It suggests something happened that we don't know about. In the early 1980s, a young physicist named Alan Guth was working on something else entirely. But he stumbled upon an idea that was meant to solve one problem, but ended up solving these cosmic puzzles as a bonus. He called it inflation. The idea of cosmic inflation is simple, but has massive consequences. It says that in the very first fraction of a second after the Big Bang, a time so short it's hard to even imagine, the universe went through a period of extreme, accelerated expansion. It didn't just expand, it inflated, it doubled in size, and then doubled again and again and again, many, many times over, all in a split second. The universe grew from something smaller than an atom to something larger than a grapefruit almost instantly. Then this super fast expansion stopped, and the more normal, leisurely expansion we see today took over. how does this solve our problems? Let's go back to the horizon problem, the uniform temperature. Inflation solves this beautifully. Before inflation kicked in, the entire observable universe was a tiny microscopic patch. Everything was so close together that it could easily share heat and settle to a uniform temperature. It was all connected. Then inflation happened. It grabbed this tiny uniform patch and stretched it out to be enormous. The two opposite ends of our sky that look so far apart now were, before inflation, right next to each other. They have the same temperature because they started in the same pot, so to speak. Problem solved. And what about the flatness problem? Inflation solves that one too. Think of the surface of a balloon. When it's small, you can easily see its curvature. But as you blow it up to be incredibly large, any small patch on its surface starts to look flat. If you blow the balloon up to the size of the Earth, the piece you are standing on would seem perfectly flat to you. Inflation does the same thing to the universe. It takes whatever initial curvature the universe had and stretches it out so much that our observable part of it looks perfectly flat. The universe might still be curved on some unimaginably vast scale, but the part we can see is just a tiny, flat patch on a much larger structure. Problem solved. Inflation was a brilliant idea. It took two of the biggest mysteries of cosmology and solved them with one elegant mechanism. It has since become a core part of our modern understanding of the Big Bang. We have even found some evidence supporting it in the fine details of that cosmic afterglow. But here's where the story takes a turn. A turn from our one universe into a multitude of them. Physicists started asking a new question. What caused inflation? And more importantly, what made it stop? The theory suggests that inflation was driven by a kind of energy field that filled all of space. You can think of this field, called the inflaton field, like a landscape with hills and valleys. The energy of the field is like a ball rolling down a hill. As long as the ball is on a high plateau, inflation is happening. The universe is expanding at this incredible rate. For the Big Bang to happen as we know it, the ball has to roll down into a valley. When it hits the bottom of the valley, the inflationary energy is converted into matter and radiation. That's the bang of the Big Bang, the start of our universe as we know it. But what if the field is not the same everywhere? What if this landscape of hills and valleys is vast and varied? Quantum mechanics, the strange rules that govern the microscopic world, tells us that things are never perfectly uniform. There are always random fluctuations, so in some regions of this vast, inflating space, the ball would randomly fluctuate down into a valley. Inflation would stop there. A pocket of space would calm down, heat up, and a new universe would be born. A bubble. Our universe would be one such bubble. But here's the crucial part. In other regions, the quantum fluctuations might kick the ball up the hill, or just keep it rolling along the high plateau. In those regions, inflation would not stop. It would just keep going. And because inflation is so powerful and fast, the regions that are still inflating would grow much, much faster than the bubble universes they spawn. The inflating space would expand eternally, constantly creating new patches where inflation does stop and new bubble universes are born. This is the theory of eternal inflation. It takes Guth's original idea and pushes it to its logical conclusion. It suggests that our Big Bang was not the beginning of everything, it was just the moment inflation stopped in our local patch of space-time. Our universe bubbled off from a much larger, eternally inflating parent space. Think of it like a pot of boiling water. The water itself is the inflating parent universe. Every now and then, a bubble of steam forms and expands. That's a new universe. But the pot of water is infinitely large and keeps boiling forever, constantly forming new bubbles. Our universe is just one of those bubbles. And outside our bubble, the water is still boiling, still inflating, still creating countless other bubbles. This is a staggering idea. It means our universe isn't unique, it's part of a multiverse. A collection of countless, perhaps infinite, other universes. So what would these other universes be like? This is where things get even more speculative, but it's a direct consequence of the theory. The laws of physics as we know them might not be fundamental. They might just be local bylaws, specific to our bubble. Think about the valley our ball rolled into. Maybe the shape of that valley determines the fundamental constants of nature. Things like the strength of gravity, the charge of an electron, the speed of light. In our universe, these constants have very specific values, and these values are finely tuned for life to exist. If you change the strength of gravity by a tiny amount, stars would either burn out too quickly or never ignite at all. If you change the charge of an electron, atoms couldn't form stable bonds and chemistry, and therefore life would be impossible. The eternal inflation model offers a possible explanation for this fine-tuning. In this vast cosmic landscape, there aren't just one type of valley for the ball to roll into. There could be countless different valleys, each with a different shape. When a new bubble universe forms, the ball rolls into one of these valleys at random. In that new universe, the laws of physics will be set by the shape of its valley. So one bubble universe might form with gravity 1,000,000 times stronger than ours. It would instantly collapse into a black hole. Another might form with the electromagnetic force much weaker. No atoms could ever form in it. It would just be a diffuse soup of particles. The vast majority of these bubble universes would be sterile, dead places. They would be born and die or expand into nothingness without ever producing anything complex like stars, planets, or life. But with an infinite number of bubbles being created, eventually, by pure chance, a bubble would form where the ball rolls into a valley just like ours. A valley that creates laws of physics with the constants set just right for complexity to emerge. A universe where stars can form, last for billions of years, create heavy elements, and allow for planets and, eventually, life. We, of course, find ourselves living in such a universe, not because it was designed for us, but because we could not exist in any of the others. This is called the anthropic principle. It's a form of selection bias. It's like asking why we find ourselves on a planet with liquid water and a breathable atmosphere. It's not a cosmic miracle, it's just that we couldn't have evolved on Mars or Jupiter to ask the question in the first place. We are here because this is one of the places where Her can support beings like us. The multiverse idea turns our universe from a unique, perhaps fine-tuned creation into a statistical inevitability. It's a profound shift in perspective, as big as the shift from believing the Earth was the center of the universe to understanding it's just one planet orbiting one star among billions. Now, we might have to consider that our entire universe is just one bubble in an endless cosmic foam. This all sounds like a great story, but is it science? The biggest criticism leveled against the multiverse theory is that it's untestable. How could we ever see or interact with another universe? By definition, they're outside our observable horizon. They are causally disconnected from us. If we can't test a theory, if we can't imagine an experiment that could prove it wrong, is it really a scientific theory at all? Is it philosophy? This is a serious and valid point. Many physicists are deeply uncomfortable with the idea for this very reason. Science is supposed to be about making predictions and testing them against observations. The multiverse seems to put itself beyond the reach of observation. However, some people have tried to think of ways we might find indirect evidence. It's a long shot, but it's not completely impossible. One idea is that if our bubble universe formed close to another one, they might have collided in the distant past. Such a collision would have been a cataclysmic event. It might have left a scar, a subtle imprint on the cosmic microwave background, that afterglow of the Big Bang. Some scientists claim to have found a potential sign of this. There is a large, unusually cool area in the CMB known as the cold spot. One highly speculative explanation was that this could be a bruise left over from a collision with another bubble universe. It was an exciting idea. It would have been the first ever evidence of a reality beyond our own universe. But further studies have shown that the cold spot is most likely just a random statistical fluctuation, a rare but perfectly possible arrangement in the otherwise uniform glow. So far, we have found no smoking gun. There is no hard evidence for other universes. So where does this leave us? We have a theory, eternal inflation, that naturally arises from our best attempt to fix the problems of the standard Big Bang. This theory not only solves those problems, but also makes a stunning prediction that our universe is just one of many. It offers a potential explanation for why the laws of our universe seem so perfectly tuned for our existence. But it's a prediction that we currently cannot verify. We are in a strange position. We have followed the logic of our own successful theories, and they have led us to a place that may be forever beyond our experimental reach. It's important to be clear about this. The idea that our universe bubbled off from another one is not a fact. It is a hypothesis. It's a compelling and elegant hypothesis born from the mathematics that describes our cosmos. But without evidence, it remains on the speculative edge of physics. Some physicists are looking for alternatives. Maybe there are other ways to solve the horizon and flatness problems that don't lead to a multiverse. Maybe there's a deeper principle we haven't discovered yet that explains the fine-tuning of the constants. Science is always a work in progress, and yet the idea holds a powerful grip on the imagination. It frames our existence in a completely new way. For most of human history, we have seen ourselves as central to the cosmic story. First, our planet was the center, then our sun, then our galaxy. Each step has pushed us further from the center. The multiverse is the ultimate demotion. Our universe itself might be nothing special. Like just one of an infinite number of outcomes, a lucky draw in a cosmic lottery. It's a humbling thought. But it's also an incredible one. It suggests that the reality we know, the 13.8 billion years of cosmic history, the trillions of galaxies, the stars and planets, is just a tiny, isolated part of a much grander, much stranger, and much larger reality. A reality that is constantly being born, constantly inflating, constantly creating new worlds with new laws. So, did our universe bubble off from another one? We don't know for sure, and we may never know. But the fact that our best science points in that direction tells us something profound. It tells us that our understanding of reality is still incomplete. The universe, or the multiverse, is likely far bigger and more complex than we can currently imagine. We have followed a trail of clues from the puzzles of the Big Bang to the theory of inflation, and that trail has led us to the shore of a vast cosmic ocean. We can't see what's on the other side. We can't even be sure the ocean is really there. But the idea that it might be changes everything. It reframes our entire existence, not as the whole show, but as a single, fleeting bubble in an eternal cosmic foam.